Hey guys, I I apologize that the other video was giving us some technical difficulties. I think that is because I was using some animations over my filled in notes because there is a lot of writing involved in these. So I was trying to save some time. Plus my stylus doesn't work very well. And I found that I should go ahead and redo this using the good old stylus. So what I did was compromise, and I have the definitions written down, no animations, and I'm going to write out the definitions, the examples. So this last section on vectors, projections, and word problems, and it's the last section we're doing, so we're going to have a test next week, and that's another reason I wanted to get this through to you, because it is one of the most difficult of the sections we're doing, because it combines everything we've done to date on vectors. Once we do a few, you'll get it, and after we go through the process and I show you the applications at the end with word problems, it will hopefully come together for you. So here's what a projection is. It is, let me go ahead and, it is used to find the total force when the vectors are going in different directions. So that means when things move, they usually move based on at least more than one force. They have their own weight, and if you've had physics, you've already heard this explanation. They have weight, they have wind, they have friction, they have all kinds of forces affecting the movement. And so what we're going to do is show you how two vectors with their own magnitude and direction can affect the movement, but we're going to make it easier finding the total force from two different vectors by using projection, and that's what this is for. So what we're going to do, let's see, is we're going to project U here onto V, and my calibration must be off, onto V. That way they're both going in the same direction, and you can total the force easier. So when we do a projection, here is the formula right here. Make sure you write that down. And what happens is we take that U vector and project it down onto the V and make this new W vector. So that's this W vector is the projection. And to keep the integrity of U, we take into account its other, so that's like the horizontal, it's like the horizontal component, and so we take into account its vertical component, and as you can see, they are right angle to each other, so they are orthogonal, which is this right here, orthogonal vectors. So U doesn't really change, but we have its projection to help us figure out the force. And so we're showing U as now a total of its projection and the orthogonal component, the complement. I like to call it the complement. And like I said before, once we do a few of these, you'll understand why we find each one and how it works in a word problem. So I'll go ahead and use the formula. Okay, with this first example. So using the formula, what we need is the dot product, U dot V, and we need the magnitude of V. And as you can see right here, V is the one that's being projected onto, and that's also going to be multiplied by v at the end, so that you have that, the direction of that angle, of that vector. So we're going to find u dot v first, u dot v, and that is doing the dot process, which is 3 times 5 plus 2 times negative 5, and that equals 5. Then we're gonna find the magnitude of v by doing the square root of 5 squared plus negative 5 squared, and that equals the square root of 50. Now, we are going to keep the radicals, because in the formula, right here, we're gonna square those anyway. So we're gonna keep it as a radical. So now we're gonna put these into the formula. So the projection of u onto v, as you can see, the v is what we're projecting it onto. We take the dot product of 5 over the square root of 50 squared times vector v, and as I reduce this, that becomes 5 over 50. See how that worked out nicely. And I'm going to go ahead and put the vector v now. Actually, yeah, 5, negative 5. But this reduces again, so I'm going to reduce that again before I multiply it. So that's 1 over 50 over 10. Times 5, negative 5. And so when you do the 5 times, when you multiply these, this is a scalar being multiplied by these, but you got to remember that they are only being multiplied by the tops, the numerators, because it's fractions. So don't multiply by both. Then this will become 5 over 10, a new vector, and negative 5 over 10, which reduces to a half and negative a half. So that is the projected vector. And as I said before, to keep the integrity, we want to know also, so the second part, we want to know what the orthogonal vector is that balances it out. So we want to know what we're going to find W2. So down here, we are going to find U is, what it's asking for is what are the two orthogonal vectors. And so the formula is from up there, W1 plus W2. So this one is much easier to do because we have U, which is 3, 2. So I'm going to just substitute that. So we got 3, 2. And we've got W1, which was 1/2, negative 1/2, plus W2. And so to find W2, we're going to subtract these. Well, let's see if I can fit that in here. W2 equals 3, 2 minus 1/2, negative 1/2. And so W2 equals 5/2, 2.5, 5/2, and 5/2. And so when you put this back in as, let me make sure that's on. Okay. U, so the final answer here, let me erase some of that. The final answer is 1/2 negative 1/2 plus 5/2 negative 5/2. There. That's the final answer. They want to know what the two orthogonal vectors are. And there you go. Next, we're going to do another example. And this one is, the numbers are not as nice. Most cases, the numbers are not going to be that great. We're going to do the same thing. We need, so I'll write that again, need u dot v, and we need magnitude of v. So u dot v is -1 times 4 plus 5 times 6. And that turns out to be 26. Magnitude of v, square root of 4 squared plus 6 squared equals square root of 52. Leave it as a square root. Projection of u onto v. Dot product, 26 over square root of 52 squared times v. So that turns into 26 over 52 times v, which turns into 1/2, and v is 4/6. This one's actually not bad. This one's actually nicer because it's got the whole numbers. I forgot about that. It's the next one that's bad. Then this one, so the final, and that's a vector. The final vector is 2, 3, because 4 over 2 is 2, 6 over 2 is 3. So that's the W1 vector. Now we're going to do our u equals W1 plus W2, and u is -1, 5, and w is 2, 3, W2, so W2 is -1, 5 minus 2, 3, which is -3, 2. Because of our operations. It's -1 minus 2, -3. 5 minus 3, 2. And so our final answer, because this is how they want the final answer, just so you know and have it in your notes, because it is an open note test. So u is 2, 3 from W1 plus our new W2, -3, 2. And if you did the dot product of these two vectors, you would get 0, because that's why they're orthogonal. All right, one more example. Same process, but in this case, if the angle, if the angle between two vectors is obtuse, the force is the opposite, but still can get a total force. So the force is going to be affected by the angle being in the opposite direction, but we're still going to figure out the projection of it, of the vector onto the other. All right, so we're going to find these projection here. This is the one that the numbers are not nice. So you've got u dot v equals -3 times 6 plus 4 times 1, and that equals -14. Yeah. Then you've got the magnitude of v equals the square root of 6 squared plus 1 squared, so that's the square root of 37. And that's one of the main reasons it's a pain because of the square root of 37. Okay, projection. We are finding W1, which is the projection of U onto V. So we take our negative 14 over the square root of 37 squared times V. And I'm actually going to go ahead and skip a couple of steps because we've already done this a couple of times. So I'm going to go ahead and put the vector in there. 6, 1, vector V. So what I'm going to do is I'm going to multiply negative 14 times 6 and negative 14 times 1, and they're both going to be over 37. So that's negative 84 over 37 and negative 14 over 37. So that's part A. I have found the projection. Part B, or step 2, is to find the other vector, the complement to this. So W2 equals U minus W1, which we have been doing. So now I'm going to fill it in. U is negative 3, 4, and W1 is this ugly thing we have here, and I'm telling you right now, use your calculator for this. If you have one that does fractions, do that. But if you have your graphing calculator, in graphing calc, use math fraction. Use the math button and then the fraction button. So you're going to do negative 3 minus negative 84 divided by 37. Then you're going to do negative 4 minus negative 14 divided by 37. It will give you a decimal, but then you go over here and use your math fraction button, and it will give you the nice decimal, or the nice fraction, which is actually really big, weird numbers. Negative 27 over 37, and 162 over 37. And so U, which is the final answer, is this plus this. All right, last slide. The word problems. So, finding the force from two directions, as we have been talking about, we're using projection into one resultant vector using projection. So this is just an example of what things look like. This is an example of what things look like. It is, in this case, they're using U as the forward motion and V as the angled motion. Most of the time your word problems are going to have somebody pushing forward or dragging something, and then the other one is going to be it's going uphill or up a ramp or something. So that's why there's two forces going on here. And so let me go ahead and go through an example with you. So to make things easier, well, let's read the question first. So Mary sits on a sled, so drawing a picture is helpful, and I actually had a nice little picture. I guess I could have kept that. And that is not a very good hill here. So we have a hill. Let me try again. Here's a hill in the shape of a nice triangle. And this is 60 degrees. 60 degrees. And Mary is sitting in a sled. I'll just draw the sled. There's the sled. And, well, there's a person sitting in it. It's really hard to draw. You can see their head I had before. Right? Okay. Whatever. What force is required to keep the sled from sliding down the hill if the weight of her and the sled is 125? So we're going to put 125 right here, pounds. And that is a force going down. And so we are trying to find, basically trying to find V. So what we are going to do here, that's degrees. We are going to start with, so let me write this down, find V as a unit vector. Can you even read that? Okay. Find V as a unit vector. I don't know if you can read that. It's hard for me to read. Which means that the magnitude of V equals 1. So we're trying to make this easier, and we can find the magnitude of V to be 1 by using the things from the second set of notes with the cosine and everything, where the magnitude times the cosine of the angle is the horizontal, and the magnitude times the sine of the angle is the vertical. So we are finding this unit vector, and this equals 1/2 n squared of 3 over 2 from our trig unit and the unit circle. We're going to use decimals, so if you get things, most of the time they're not going to be like 60, 30, 45 degrees, so you're just going to get decimals, which is fine. All right, so this is V, our unit vector V, because it's not the actual V we're looking for. And so what we are going to do, we are now going to find the projection of F onto V. Now what is F, you might ask? Well, that's going to be the force here. So we're calling this F. And if you remember from our one of our last word problems, if I draw a coordinate plane on here, this point here at the bottom of the 125 force, that's going to be F. And that's going to be 0, negative 125, because it's pushing down, and so that's going to be our F vector. And so that's how we're going to find F projected onto V. And I'll tell you about that. It's going the opposite direction, so we're going to show you that in a second. Okay, so back to our problem here. We're finding the projection. And you find that we need the dot product of F dot V. So we're going to do that. F dot V means 0 times 1/2 and negative 125 times the square root of 3 over 2. Now this turns into 0. So we have an answer here of negative 108.3. So what we have found is just the projection so far. But the funny thing is, if we go ahead and finish the projection and put divided by 1 squared, because that's the magnitude, times the unit vector which we just multiplied by, it basically all cancels out. And since it is a unit vector, we are going to use this value, but we have to use it in the opposite direction because before F was going down, so the force we're going to use kind of cancels itself out, especially with the unit vector. So your answer is just the positive of this. And I will direct you to the book if you want a better explanation, because I know that probably didn't make a whole lot of sense, but that's the answer. That many pounds. And since this is like the 5th time I've done this video, including my practice rounds, I'm hoping that this one works this time. Make sure you ask me if you have any questions, and I am going to be doing some detailed problems. Hopefully I'll have my new stylus by then. Thanks for doing your work and giving me feedback.